Mirrors. Here are your priming questions. To begin with mirrors, we have to start with the law of reflection. For this, it's pretty simple. The angle of incidence, so the angle that it comes in at to the mirror, equals the angle of reflection, how it bounces off of the mirror, as measured from the normal. And hopefully you remember back from first term, the normal is the perpendicular to the surface. So what you need to remember is that we always measure our angles from the normal to the surface. Okay, this will become very important when we talk about refraction later on and we work with the sine of the angle. If you don't use the angle from the normal, you won't get the right answer. And so whenever light comes in and hits a surface, the angle that it reflects at will be dictated based off of the law of reflection. Now for a plane or a flat mirror, you can see what happens with the light rays. So as the light rays extend out to the mirror, when the light rays reflect off, they will all obey the law of reflection. So we could draw these normal lines here. Now in this case, because they all diverge on the reflection, we have to draw the extensions behind the mirror, and we'll go a lot more in depth into this with our ray diagrams. And what happens is, when we draw these extensions of the reflected rays behind the mirror, we can see where they converge, and that's where the image will be located, behind the mirror. Which brings us to here. Whenever the image is behind the mirror, we form a virtual image. This image, since it's behind the mirror, obviously is not there. This image is formed in our brains when it receives these rays of light reflected from the mirror, and our eyes collect that data, and then our brain formulates the image, and we perceive it to be beyond the mirror. So the next time you go to the bathroom and you look at the mirror and you see the reflection of yourself, if you think about it and really pay attention to it, it appears that your reflection is inside the mirror or behind the mirror. It's not really there, but that's where our brain has combined these visual rays of light to form the image in our brain as behind the mirror. Now for a flat mirror, the object size equals the image size. So that would be the height here. Also, the object distance from the mirror is equal to the image distance. And in this case, a plane or a flat mirror does not change the magnification of the object. So the image has the same size, it's the same distance away. And it is upright, so you'll notice that it is not upside down, and we'll show you some examples later on of some images that can be upside down. And if you've looked at special mirrors, in some cases it appears that the image is upside down. Which brings us to spherical mirrors now. And the name is very descriptive. For right now, we are keeping our mirrors simple, and we're only going to be talking about flat mirrors or spherical mirrors. There are many other different types. There are parabolics, there are different curvatures, but we are going to keep things simple and talk only about spherical mirrors now, as well as the plane mirrors from before. And the way to think about spherical mirrors is they are just a section of a sphere, if we were to consider the whole thing to be a sphere. And so these mirrors are going to have a curve to them, and we can describe the curvature in terms of the center, there's going to be a focal point, the radius, and what we call the vertex. And so those will be some of our new terms. The principal axis is going to be the line that we are going to be placing our object on. The curvature, or the center of curvature, if you were to imagine the mirror as a sphere, the center of curvature would be the geographic center of that sphere. The vertex is where this principal axis meets the mirror. The focal point is going to be halfway between C and A, the center of curvature and the vertex. The radius of curvature is going to be the distance between your center and your vertex. And the focal length is going to be between the vertex and the focal point, which is going to be half of the radius. So hopefully this diagram will make more sense with that. So again, this is part of our mirror. And if we were to imagine this all as a sphere extending out, the C would be the center of that sphere. F would be halfway between C and where the radius hits the vertex over here. The radius is there, and the focal length is there. And this will hold true for both concave and convex. Right now, we're going to focus mostly on concave mirrors, though. Concave mirrors are what we call converging mirrors. So if you look at this diagram on the left, you can see that parallel light rays, when they come in and they hit the mirror, they will converge together, and you can see that it's through the focal point. So that's the first principle for concave mirrors. Any incident ray traveling parallel to the principal axis, when it reflects, it will go through the focal point. We're going to use this idea for our ray diagrams later. And the other part of this is any incident ray passing through the focal point initially, after it hits the mirror, it will then reflect parallel back, parallel to the principal axis. Now, there are some pretty interesting things that happen when you work with spherical mirrors. The first is called spherical aberration, and this is the first one that we're going to talk about, and we'll talk about some other things in some subsequent videos. If this happens, you can actually get a blurred image because you have too many light rays reflecting, and they are not going through the focal point. And when this happens, you get multiple images formed, but because they're not going through the focal point, they don't focus correctly. And so the way to fix this is to actually block those light rays that will not go through the focal point, so that only the ones that go through the focal point are the ones that form the image. And so if we were to draw the rays for this, and let me use the arrows for this. So if we were to draw the rays of light for this, we could draw the ones that we know for sure, parallel, and then through the focal point, which would be there. And the ones that we are worried about for the blurred image, if we are going at an angle like this, it is not parallel and is not through the focal point, and so we would have to use the law of reflection and measure the angle here, but it would not be passing through the focal point, which could be over here somewhere. And because it's not passing through that focal point, this ray, when it reflects, could be going in many different directions, and that's what causes our spherical aberration. Now, for our equations, we have the mirror equation, 1 over the focal length is equal to 1 over di plus 1 over do. And for these, we'll go ahead and say that we want these to be in meters. And for our magnification, the magnification is equal to these two ratios potentially. So the ratio of the heights or the ratio of the distances. So the height of the image over the height of the object, or the negative distance of the image divided by the distance of the object. And you'll see the significance of the negative here. And we'll talk more about that later in class. Here are your priming questions again.